Hey everyone, hope you're doing well at home. My name is Frank Ong, and today I'll be talking about some very exciting work that we've been doing at Stanford and Berkeley. It's about an improved SLR algorithm. It can let you generate pulses with up to 26% lower energy and also more accurate phase profiles. Our group receives support from GE Healthcare. So the Shinnar-Le-Roux algorithm, or the SLR algorithm, has really been the gold standard for designing frequency selective pulses with large flip angles. Since its development in the late 1980s, scanners worldwide have used its pulses for a wide range of applications. Now, people like SLR because it's very simple and also very effective. But it turns out we can do better. Now, how is this possible? So there's two parts to the SLR algorithm. The first part transforms an RF pulse to a pair of polynomials. The two polynomials represent the so-called Cayley-Klein parameters, which are used to represent rotations. Now this transform is invertible, and it basically converts a highly nonlinear pulse design problem to a polynomial design problem. So this part is good. Now given the invertible transform, in the second part, we want to design some Cayley-Klein polynomials to match our desired magnetization profiles. Now this is the part that's not quite perfect yet. You see, the Cayley-Klein parameters are bilinearly coupled in the design. So for example, MXY, the transverse magnetization, is related to the Cayley-Klein parameters alpha and beta as 2 alpha conjugate times beta. So to solve for the Cayley-Klein parameters requires us to basically solve for a bilinear inverse problem. But the issue is solving a bilinear problem back then was quite difficult. So the original SLR algorithm did not jointly solve for the polynomials. Now it turns out recent development in convex low-rank matrix factorization techniques has enabled us to tackle these problems. Just to make the connection to low-rank matrices a little bit more explicit, we can look at the following matrix vector representation. On the left, we have our usual MXY and MZ vector. Then we can rearrange the vector into a 2x2 matrix shown in the middle. On the diagonals, we have 1 plus MZ and 1 minus MZ. And on the off diagonals, we have MXY and MXY conjugate. Now this kind of a matrix representation is often called a quaternion. And there are many nice properties about quaternions. One of them is that whenever the magnetization vector has unit norm, which is the case that we're considering, then the corresponding quaternion has rank 1. And it turns out the rank 1 factor here is what we call the Cayley-Klein parameters. And for more details, I encourage you to visit the following links for preprint and code. But first, here are some results comparing the original and the proposed SLR design. These are linear phase excitation pulse with a time bandwidth of 8 and a ripple of 1%. If you look at the pulses on the top left panel, you can see that the proposed SLR pulse has a lower peak amplitude compared to the original SLR pulse. This is also reflected in the energy reduction, where there's an 18% reduction from 0.318 to 0.259. Moreover, if you look at the phase profiles on the lower right panel, you can see that the proposed SLR pulse has a much flatter profile compared to the original one. Here's another result with minimum phase inversion pulses. Pulse energy is reduced from 3.0 to 2.31, which is a 23% decrease. Note that the improved pulse also has fewer discontinuities near the edges, commonly known as the Connolly wings, when compared to the original SLR pulse. So in conclusion, we've shown an improved way of designing SLR pulses by jointly solving for Cayley-Klein polynomials using low-rank matrix factorization. Again, for more details, I encourage you to visit the following links for the preprint draft and also code. Thank you.